A pleasant morning to everyone who have joined us today for the day one of 3-day national level faculty enhancement webinar series organized by EEE Department, MEENAKSHI Sundarajan Engineering College. We have a couple of minutes left for the session to start. Before that, I request our department head, Mrs. Soundarabala, to share a few words about our webinar. Over to you, ma'am.
Thank you, Gayatri. A very good morning and a warm welcome to all the participants who have joined in today's webinar. We have participants from across India and rest of the world as well. This is our first webinar series and this is an initiative by the Department of EEE of MEENAKSHI Sundarajan Engineering College. This coronavirus outbreak has disturbed everything, including how we engage with our network. During this crisis, we thought of utilizing our strengths and our connections with the brilliant minds of our industry to bring amazing insights to the participants and our members who all are participating in today's webinar. We have chosen this topic, Technologies for the Effective Use of Modern Power Systems, of this 3-day webinar series, focusing on the modern power systems. We hope that today's webinar will bring it will be relevant and helpful to all our participants. My hearty welcome to our today's speaker, Mr. Krishnakumar, who has agreed to be part of this webinar and share his knowledge through this platform. I welcome you all once again.
Thank you, ma'am. Now, we would like to introduce our proud alumnus and his achievements through a small video. I request our technical team to play introduction video of our resource person, Mr. Krishnakumar. It is always a great feeling to see our alumni succeeding in their professional lives. We are happy to have him here for the session. Without any delay, I hand over the session to Mr. Krishnakumar. Over to you, sir.
A very good morning, everyone here. I hope all are doing good amidst this global pandemic we are facing. And I believe there are experts from microgrids and energy storage systems also in the room. And please allow me to share my little experience gained over these years with microgrids and energy storage systems. So let's get started. So in today's session, we will see about a brief history of power system and its transition from various stages followed by various components of microgrids like distributed energy sources, energy storage systems, and we will also see the control strategies which are underpinning the microgrid stable operation, followed by various challenges in the microgrid and few success stories and in India itself. So as you look at the history of power system, the first ever power system was started with a hydro turbine in 1881 in England, and it powered 7 arc lamps and 34 incandescent lamps. Followed by which, on the other side of the Atlantic in 1882, they had their first ever steam power plant at Manhattan, and later in 1885, there was an invention of AC transformer, which made the AC transmission viable. And in 1881, 1888, there started the war of currents between Edison and Tesla. And later on in 1895, no other go, three-phase AC power generation was commissioned at Niagara Falls. So if you see at the history of power system, initially it was a distributed one which was scattered around the globe, and later it transited to a centralized one. Now the power system looks something like this, where we have centralized generation sources connected to either transmission or sub-transmission levels, and we have tap points from the distribution substation. And if you look at the power flow from the generation to consumption point, it is always unidirectional in the centralized power system. So we will see what the transition has, why the transition has occurred from a distributed to centralized one. Firstly is the location of power system, which is away from the load center, because all the power plants were located close proximity to the fuel reserves or near the ports for easy logistics of fuels. And also, of course, they need enormous amount of water for their operation of steam power plants or nuclear, for anything that matters. And bulk power generation seemed to be economical over scattered distributed power plants, and reliability of such power plants were very high because of its ability to ride through contingency events, where there is a possibility for inter-area power flow. And one more important thing is the use of old power plants for peak load demands. In such a case where the power plant's efficiency is too low for an old power plant, it can be used for peaking load, for meeting the peaking load, so as to defer investment in generation. So the future power system, or the power system which is transiting to the decentralized one, looks like this, where we have sources or renewable energy sources located along the distribution systems, and there will be a bidirectional power flow and as well as communication flow. And all these were facilitated by the smart grid paradigms or communication infrastructure, which again is it will take some time for the transition to occur, but future power system will look something like this, where we are transiting to decentralized power system again. And the cost for transition from centralized to distributed remains one of the major cause is transmission losses in a centralized grid. In the next slide, we will see some statistics of transmission losses of the countries around the world. And distributed generation offer high resiliency with the operation in islanded mode, and also it improves the end user participation with as the consumers are able to decide when to consume their power and when to feed it back to the grid. So this is global statistics of top 5 countries with the highest installed capacity. You can see China is the top, and the transmission losses is just 5%, whereas India stands third, and the transmission loss accounts for 19% of their system capacity, which is very high actually. 19% of 64 gigawatt is enormous amount of energy wasted. So we will move on to microgrids. We'll see what is a microgrid. US Department of Energy defines a microgrid as a group of localized generation and loads which can act as which are perceived as a single entity from a grid point of view and can be controlled as a single entity. And in such a case, these microgrids can operate in both grid connected mode and also operate in islanded mode. Islanded mode by mean it can disconnect from the grid and still power its local loads. So a typical microgrid looks something like this, where you have different renewable energy sources starting from different sources, starting from renewable energy sources to fossil fuel like micro turbines, and we have a localized loads also with energy storage systems and a supervisory control system. And protection systems are inherent for any power system, so they are inevitable. Whereas we do have power converters to synthesize the power from various renewable energy sources, and we will see what are the stages of conversion and types of converters used in different types of renewable energy sources in the next upcoming slides. So what is the need for power electronics? First thing is the nature of output. The renewable energy sources can generate output either in DC or AC form. If it's a DC, we need, of course, a conversion system to convert to AC to feed our loads. But even though if the generation is in AC, they are not at nominal frequency and nominal voltage level. So we need to convert a non-grid friendly AC to a grid friendly AC. So that is the second need, and following which maximum power point extraction from renewables. All renewable energy sources have a maximum power point in their performance or operating region. All these are achieved through maximum power point tracking algorithms, which manipulate the switching of power converters which in turn modifies its output impedance of the converter or the sources. And these power converters enable decouple control of real and reactive power, which again results in voltage and frequency regulation. So these are the main aspects of power electronics, which why it is needed in a microgrid. So we have all types of sources which are used in a microgrid, and it's not limited to renewable energy sources. We do have biomass, diesel generators, or micro turbines, which uses fossil fuels, but they are also called as distributed generation sources. So if it's a renewable energy sources, it's well and good for a microgrid. But if it's if there is a need for micro turbine and biomass, then it is also called as distributed generation sources. And one good thing about these fossil fuel powered generation systems are its ability to support the renewable energy sources. So we can upsize the renewable energy sources and downsize these fossil fuel based power plants or generation systems just to maintain the stability of a microgrid. So we will look into details in the next slides. So first we have a solar PV system where the solar panels convert the solar irradiation into electrical energy through photovoltaic effect. And as you see, the output of solar PV is always DC in nature. So which by large, most of the microgrids are AC in nature. So we need to have a DC-DC conversion stage, because this DC-DC conversion stage usually incorporates maximum power point tracking algorithms, which tracks maximum power point for the particular irradiation. And of course, the DC-AC conversion stage converts the DC to grid-friendly AC, and usually the DC-DC converter also performs another function, which is boosting the DC link voltage. It's because suppose if the line voltage is say 400 volts, you need to have a DC link voltage at least 1.7 times as that of the line voltage. So you need to have at least 700 volt at the DC bus to invert it to 400 volt AC. So that's one of the main reason we usually go for two-stage conversion process. Then we have solar thermal generation, which is quite interesting than the solar PV one, because these thermal generations are similar to our steam generation, whereas the mechanism of generating steam differs in this. We use solar irradiation to generate steam and drive a steam turbine, which is connected to the generator. So in this case, we have a central. Again, these solar thermal power generation schemes vary based on different configurations. This particular configuration is basically we call it as central tower configuration, where heliostats or reflectors are used to focus the solar irradiation to a central tower where there is a working fluid. It may be a water for a normal Rankine cycle, or it may be other hydrocarbons or organic fluids for organic Rankine cycle. Organic Rankine cycle is used when the irradiation is less in that area, or the temperature can't exceed 350 degrees centigrades to generate superheated steam. So in that case, we go for organic Rankine cycle. So the rest, once the steam is generated, the rest of the plant remains similar to our thermal generation plants. Another variation of solar thermal generation is using linear Fresnel collectors. These linear Fresnel collectors differ from the previous heliostats by its operation, as they are called as point focus systems. These are called as line focus systems because the pipes which carry the working fluid runs through the axis of these Fresnel collectors, and the solar irradiation is focused to the pipes along the length of the pipe. So this is called as line focus systems. And again, the rest of the plant remains same for most of the thermal generation plants. Our wind energy conversion systems, as India is one of the highest potential for wind energy conversion system, and it's one of the largest producer of wind energy conversion. And in case of a microgrid, we need not go for a large wind turbines. We usually go for micro turbines, or which is of kilowatt capacity based on the loads. And again, microgrid is not defined by its capacity. It's rather defined by geographical boundaries and electrical boundaries. So we can also use large wind turbines to power a large community or a large urban area. So we have two variations of wind energy conversion system, one being fixed speed and the other being variable speed. If it's a fixed speed, there is no problem. You need not have a power converter. You can directly connect the generator to the grid. But the only problem with the fixed speed generation systems are the limited operating region. The operating region is limited by its narrow wind speed, narrow region from cut-in speed to cut-out speed of operation. Whereas in a variable speed wind energy conversion system, these turbines have low cut-in speed, so that these power converters can convert the non-grid friendly AC to grid friendly AC. And usually, to track the maximum power of wind energy conversion systems or wind turbines, set of back-to-back topology is used, where we use voltage source converters in a cascaded fashion to form a DC link in between. And the rotor side converter usually performs the maximum power point tracking operation, whereas a grid side converter is usually to maintain the voltage and frequency at nominal values and take care of the harmonic injection. The next one is our micro turbine generator. Micro turbine generators are nothing but they are similar to our jet engines, where a fossil fuel, natural gas, or biogas are used to combust in this combustion chamber and used to drive a gas turbine. But one problem with this is it requires a high-speed generator, because the revolution speed of gas turbine can go as high as 90,000 RPM to 120,000 RPM. So in such a case, we of course need power electronics to convert it into a grid-friendly AC. And it does employ the same power converter configuration as that of variable speed wind energy conversion systems. But the rotor side converter doesn't have any maximum power point tracking, because the turbine itself operates at highest efficiency all the time. So we have done with the basics of distributed generation sources. We will go on to the critical entity called as energy storage systems, which are predominantly the supporting systems of a microgrid. I'll tell why I say supporting systems in the later slides. So what is an energy storage system? An energy storage system is nothing but a device which stores energy when there is a surplus power in the grid and delivers energy when there is a deficit of power in the microgrid. So they act as both controllable loads as well as controllable sources for this matter. So they are very critical for the stable operation of microgrid, as most of the sources of distributed generation are renewable in type, which are stochastic in type. So the energy storage systems are basically classified into various using various criteria, but here we will just see a a classification based on medium of energy storage, which starts from mechanical, electromechanical, electrochemical, electrical, thermochemical, chemical, and thermal energy storage systems. We will briefly look into few energy storage systems which covers all these categories, and again, let's move on how these perform the supporting operation of a microgrid. First thing is the pumped hydro storage. Pumped hydro storage are predominantly the largest type of energy storage system which are tried and tested for so many years. And throughout the globe, the highest they occupy the highest share in energy storage system with a capacity of about 168 gigawatt, as opposed to meager 4 gigawatt of other energy storage systems. So these pumped hydro storage systems have or similar to a hydro power plant, we have a lower reservoir as well as an extra retrofit. So what happens is, during generation mode, the water flows from high reservoir to the lower reservoir and turbine generates power. When there is a surplus power in the grid, the water is pumped from the lower reservoir by operating the turbine pump unit in pumping mode, and water is pumped to the upper reservoir and stored it as a potential energy. So by exchanging water from high reservoir to the lower reservoir, energy is either generated or stored using pumped hydro storage. We have another variation of pumped hydro storage, which is variable speed pumped hydro storage, where we employ back-to-back AC-DC and DC-AC converters. It is mainly because pumped hydro storage are they require flexibility in both the modes of operation. So with variable speed operation, pumped hydro storage can offer flexibility up to 30%. That is, they can perform satisfactory pumping using 70% of the rated power itself. And in generating mode, there are various hydraulic and mechanical constraints stipulated to the turbine. And these constraints are usually overshadowed by the operation of hydro storage in variable speed mode using the power converters. Battery energy storage, again, a common type we all know, but so we won't discuss much in deep about this. So we will just see what the power converter does in a battery energy storage system. When the battery energy storage system needs to inject power, the DC-DC converter operates as a boost converter, and the DC-AC conversion performs the grid integration. The DC-DC converter in this case is a bidirectional converter, where in charging mode it operates in buck mode, and in discharging mode it operates as a boost converter. So the next type of energy storage is thermal energy storage. Sorry, I forgot to mention about one more criteria of classification, which is based on the energy and power capacity. Power capacity of energy storage system is nothing but if their capability to discharge at the rated power is called as power capacity, whereas high energy storage is the one which stores energy for several hours of autonomy or even several months using pumped hydro storage. So these high energy storage systems usually used for seasonal storage or maybe autonomy for a few days. But high power or high power capacity energy storage systems are usually used for meeting various dynamic changes in the system. So far, these are high energy storage systems which are used for autonomy of several hours. We will see few more high power capacity energy storage systems. So you will get to know what are the major difference. With the thermal energy storage generator, when there is a surplus power in the grid, the generator usually generates power and dissipates heat in the resistors, and it is stored in a pressurized container and thermally insulated container. And the heat exchanger performs the exchange of heat to the steam generation system, and in turn drives the steam turbine. So there are different types of thermal energy storage systems where they use latent heat and sensible heat for various functions using various thermodynamic cycles. So it is high energy storage where you can store energy for several days also. Then comes the compressed air energy storage, which is also a high energy storage where it consists of a set of turbines, compressors and motor generator or a machine, and also power converters. What happens is when there is a surplus power in the grid, these compressors operate and compress the air and store it in underground cabin or overground tanks for storage. And once there is a need for energy, this compressed air is let into a combustion chamber, and after the combustion of fossil fuel, the hot air is used to drive the high pressure and low pressure turbines. And since, as we have seen, gas turbines always run at high speed, we need a power conditioning unit. Here we go for AC-DC and DC-AC conversion stage. And again, this AC-DC conversion stage at the machine site doesn't have any maximum power point tracking, as these turbines operate at highest efficiency as possible every time. And another important storage is hydrogen storage and fuel cell. This is a combination of two or three subsystems where we have a electrolyzer, a hydrogen storage, and a fuel cell. The electrolyzer operates as a charging device where it consumes electricity from the grid and electrolyzes the water, split the water into hydrogen and oxygen. The generated hydrogen is stored in a compressed or pressurized hydrogen storage, and the stored hydrogen is used to generate power using a fuel cell when there is a need in the grid. And since the nature of power injected or power absorbed is in DC, we need a DC-DC conversion and a DC-AC conversion stage. And this is one of the high energy storage which is gaining attention among the researchers and also among the various governments of the world for large-scale integration of energy storage. So the next energy storage is superconducting magnetic energy storage. We all know that a conductor can store its energy in its magnetic field, but it dies down due to the presence of resistance. But in case of a superconductor, when it's cool below its critical temperature, the resistance becomes zero, and the magnetic energy is stored in the magnetic field without any loss. So we need a refrigerator system to maintain the temperature of the vacuum insulated vessel where the superconducting material is present, and it is predominantly kept at below the supercritical temperature. And we need a power conditioning stage of DC-DC to DC-AC because the energy is stored in DC magnetic field. So the DC-DC also performs boost operation where you need a higher DC link voltage for interconnecting with the grid. And mention it comes under high power storage because it can deliver power at it can deliver the rated power at within a few fraction of seconds, say within a millisecond once the power is demanded. But it can't discharge for several hours. Their discharging time is limited to say 2 to 3 minutes of operation, and it dies down after 2 to 3 minutes. So flywheel energy storage also comes under high power storage, where a stainless steel flywheel or a carbon fiber flywheel is used to store energy in its moment in its inertia through kinetic energy. So once there is a surplus power in the grid or microgrid, the generator or motor units absorb power and the flywheel is rotated and the energy is stored in the stored as a kinetic energy. When there is a need for sudden burst for energy or sudden burst for power, the flywheel is operated to deliver power. And As you see, all these power conversion stages are bidirectional power flow, indicated by the doubly directed arrows. Since it needs to facilitate power flow in both the directions, and we have AC DC and DC AC conversion as most of the machines used in the flywheel energy storage or of DC in nature. They don't use DC machines for this. And in case of a very high speed flywheel energy storage, they use magnetic bearing for magnetic levitation in order to reduce frictional losses in the mechanical bearings. So we have another class of energy storage called supercapacitor. Similar to conventional capacitors, only distinction lies between the formation of double layer. The double layer is formed by the porous electrodes at both the end and separator in between the electrolytes. What happens is the formation of double layer increases the energy capacity of a supercapacitor. Usually the discharging time for our normal capacitors is maybe 1 or 2 seconds. It discharges the full power, whereas a supercapacitor can last its power for about 30 seconds or 40 seconds. That's the maximum which supercapacitor can also store. So this comes under high power category as well. So I've seen most of the energy storage systems, and most of the energy storage systems are high power in nature and also high energy in nature. None of the system has both the capability. So either they have a high power or either they have high energy. And every application demands an ideal energy storage, which demands both high power and high energy. For this, what people have started doing is they have started combining one or more energy storage systems to form a hybrid combination so that it operates as an ideal energy storage for such an application. We will see what is hybrid, what is the need for hybrid. I'll say you when we go on for control strategies of microgrid. So we will see the operation of microgrid, where we have a on-site generation in the marked area and a fault occurs at the substation level, at the distribution substation. What happens is, once the fault occurs, sorry, I think the animation is not working here. So I'll just explain. Once the fault occurs, the microgrid controller isolates the marked area to its islanded mode and continues to power its load using the on-site generation. So with a microgrid, you can have high resiliency of operation to the load. So if we move on to the types of microgrid, we have first classification is based on the type of bus or the type of interconnection we usually have with the load. It's either DC or AC, or it can be even hybrid microgrid. Here I have shown a hybrid microgrid with AC as well as DC subsystems, where people are preferring DC because of to reduce the extra power conversion from DC to AC for most of the renewable energy generation or energy storage systems, leaving flywheel or variable speed wind energy. So solar, all the battery energy storage systems, fuel cell generate DC. So people are going for dual combination of AC bus and DC bus to form a microgrid, hybrid microgrid. In hybrid microgrid, as we see, there is an interlinking converter in between, and a lot of research has been put on developing control strategies to control this interlinking converter so that both the operation of AC subsystem and the DC subsystem remains efficient enough. And one of my friends also is researching on the control of this type of microgrid, which is of hybrid in nature. I hope he's also in the session. So another classification of microgrid is based on the location. It can be classified as either urban microgrid or rural microgrid or even industrial and military microgrids. So we will move on to control of microgrids. I know it's quite rushing, but I'll try to cover most of the aspects of microgrid, where at first we have seen the different sources and different entities of microgrid. Now we will go for control strategies of microgrid. Okay, microgrid control takes place in a hierarchical fashion where we have different levels of control, starting from 0 to level 5. But level 5 comes with the logistics and supply chain management. So we will not go in detail about the 5th level. We will stick to 3rd level, 2nd level, 1st level, and 0 level. There's no 4th level because 4th level comes into picture with the grid operator. So we won't be dealing with the 4th level control. We'll stick to first 0 to 3 level controls. So to mention here, the 0th level control pertains to controlling the distributed generation, and the 1st level control pertains to maintaining the frequency and voltage, and the 2nd level control is the one which sets reference frequency and voltage reference for the below 2 levels of control. And the 3rd level control, which is a tertiary control, maintains the operation of microgrid, maintains the optimal operation of microgrid, and allows different configuration with respect to the grid. So I'll try to explain role of hierarchical control using a frequency regulation. So if you see when there is a sudden increase in load or sudden loss of generation, the frequency usually drops. The initial drop in frequency is arrested by inertia of the rotating machines. But unfortunately, we don't have rotating machines. We will see what are the effects due to that. The role of primary response is, or the primary control is to arrest the frequency and maintain the frequency within the stipulated limit of the grid code, which is usually, I think, 49.7 to 50.2 for Indian grid, and it varies where the other countries even have a stringent frequency limitations. And the role of secondary control is to restore the frequency back to 50 hertz. So it can last from 60 seconds to several minutes. And then after several minutes, or even if the frequency is still, if the frequency has some deviation, the tertiary control comes into picture. So let's see what is inner control or zero level control level does. Okay. So based on this, we have 3 types of converter configuration to operate a microgrid. One is grid forming converters, which is operated in voltage control. Then we have grid supporting converters. It can be either operated in voltage or current control mode. Then we have grid following controllers or converters. We have that is operated in current injection or PQ control mode. We call it PQ control mode. And in case of an isolated microgrid, there would be at least one grid forming converter to set the frequency and voltage reference. And these converters are usually fed by stable sources like diesel generator or fuel cells or any other energy storage system which can deliver power for a longer duration. Whereas the grid supporting converters plays the role of regulating the frequency and voltage. And predominantly these are also stable sources like energy storage systems and diesel generators or even fuel cells for that matter. And finally, we have grid following converters. These types of converters are usually employed with the renewable energy sources, where we try to extract maximum power throughout the operation of renewable energy sources, so that we don't lose any power untapped from the renewable energy sources. So then we move on to primary control of microgrid. The objectives of primary control is to stabilize the frequency and voltage, and it is mandatory because once the frequency violation occurs, then the stability of microgrid is imperative. It's very hard to restore the frequency once it has gone below a certain level, and all the inverters will lose out of synchronism. And voltage stability also matters because below a certain voltage, all the inverters pull out of synchronism, and it will lead to blackout of microgrid. And the primary control should also facilitate plug and play capability of distributed generation sources. plug and play capability means the DGs must be able to connect and disconnect anytime the microgrid controller wants or the tertiary controller wants. So the primary control does that, and we need to avoid circulating currents among the parallel converters to avoid overcurrent flowing through it, and which may lead to damage of the converter itself. So in the primary control, we have two categories. One is with communication or centralized control, and the other one is without communication or distributed control. The control which with communication is usually called as active load sharing, where we have different categories. The first one is called as centralized control, where the load is equally shared by all the sources and the current references to all the converters remains the same. Even if you have solar, wind, fuel cells, or any type of source, or any with power capacity, it sees to that it doesn't violate the power maximum, as well as the load is shared equally. So that's the main function of centralized control. In master slave control, we have one grid forming converter or a master, which sets frequency and voltage reference to all other converters. The other converters follow the command of the master. So this is master slaves topology. We have average load sharing. Average load sharing is similar to our centralized control, where the current is shared among the converters, but here they use weighted average current. It's based on the individual converters reference. It's because in this case the deviation of power or the power injected remains less because of the as it takes the weighted average current into action or consideration. And finally we have circular chain control, where we have, suppose if we have n converters, the n minus 1th converter determines the current reference for the nth converter, where the whole converters are formed as will be formed as a chain to control. The major advantages of these communication-based controls are accurate power sharing, which results in accurate frequency and voltage regulation, but it results in high cost for reliable communication link, and it also requires complex control structures. I have said it simply in the previous slide, but when you look deeply into all those control strategies, these communication-based control strategies are quite complex in nature as compared to the decentralized one, which we'll discuss later. And they have low reliability because even it's vulnerable to the single point of failure mechanism. If the communication channel fails, there is no way to share the power command from the centralized controller to the sources. So these are the disadvantages of centralized control. Then we have decentralized control, which is a simple group control. This group control is adapted from our normal thermal or hydro generation plants, where we use power frequency group and voltage and reactive power relation. For example, I'll explain with the power and frequency group. Suppose if the system is operating at omega naught, and due to the sudden loss of load, the frequency increases to omega 1. Sorry, it's not shown in the figure. Say it increases to omega 1. The controller has to ensure that the power is reduced to Pi, so that to restore the frequency to omega naught. So this is how group control works, and there are various types of group control realized so far, and I have attached all the citations to these different slides. Once the slides are available to you, you can use these citations to have a deeper insight of these control strategies. So advantages of these decentralized control or simple control structure, because it's only one gain which is going to decide whether the source has to increase its power output or decrease its power output based on the frequency of the grid, and it is highly reliable due to the absence of communication link. And however, it does come with limitations, and these are not, I won't say it as serious limitations, but it does affect the performance of the system. First thing is the degree of freedom is limited to 1, since the only control variable in a Drup coefficient in a Drup controller is a Drup coefficient. So in order to achieve it, they contribute both frequency and voltage regulation and also response of the system. So it's very difficult to achieve a trade-off between response and steady state deviation or frequency regulation. And one more important thing is these Drup controls for inverters or converters are derived assuming high output inductance, which is predominantly not the case with the microgrids, where the resistance dominates the inductance. So various modifications has been done to the Drup techniques so that it also ensures accurate power sharing in a highly resistive network. And you can find those details in source number 9, which is by Professor Joseph Guerrero. Then we move on to the secondary control. The objectives of secondary control remains simple as it has to restore frequency and voltage of a microgrid. And we have variations here, which is centralized and decentralized. And what are advantages and disadvantages we have discussed so far for centralized and decentralized control pertaining to the primary control also applies for secondary control. So this is a centralized secondary controller where the secondary control itself lies within the microgrid central controller. And through a communication channel, it shares the frequency and voltage reference to the different sources of a microgrid. And the inner loop takes care of the regulating mechanism. And this is a decentralized secondary control where you have a separate secondary controller for every source, which is reliable, but again, the control actions are limited to, the degree of freedom is limited to 1. So that's the problem with decentralized secondary control. We have come to the top of the control hierarchy. We call it as tertiary control or energy management system, or even it is called as a microgrid central controller. Based on the configuration of secondary controller, secondary controller can be clubbed with tertiary controller to form microgrid controller, or if it's a decentralized one, it still remains tertiary control only remains in the microgrid central controller. The objectives of tertiary controller varies as based on the configuration or interconnection of microgrid with the grid. For a grid connected mode, the control is simple. It only controls the power exchange with the grid, when to exchange the power with the grid, and detect the problem with the upstream network and isolate the microgrid itself. And it has to just follow the voltage and frequency set points set by the grid operator. So it doesn't have any headache on setting voltage and frequencies. So whenever a microgrid is connected to a grid, it has a stiff source to support its voltage and frequency. So the microgrid controller need not worry about voltage and frequency, whereas it has to see to that the operation of microgrid is optimized through exchange of power between microgrid and the grid. The exchange of power, and again, it depends on the different criteria. It may be because of if in a dynamic pricing environment, then it can be because of the low price. They consume power from the grid, and when there is a high price, they inject power to the grid. I'll say what is that in the next slides. And in islanded mode, the control becomes tedious, where it has to perform all the operation and control scheduling which is required for operating a traditional power system. So it has to set both the frequency and voltage reference to the lower level control. It has to perform day-ahead scheduling. It has to perform real-time dispatching of DGs. So the control becomes tedious for a tertiary controller when the microgrid operates in islanded mode. And it's not easy to operate a microgrid, as we have different challenges in a microgrid. And the first issue is the stochastic generation of renewable energy sources. Due to this stochastic generation, renewables are treated as non-dispatchable sources as opposed to the normal thermal or hydropower plants. So even if they can be controlled with MPPT controller, but still if it operates in off MPPT control in case of a over frequency event, it reduces the overall efficiency of the system. And the second thing is the small signal stability. These microgrids are prone to or vulnerable to frequency and voltage excursions for even a small change. And of course, no issues on rotor angle stability due to the absence of rotating machines. And so the probable solution for these stability issues is to integrate energy storage system with the microgrid. What does a energy storage system does? It solves the intermittency problem of renewable energy sources and offer good load following capability. Followed by it ensures power quality, high power quality, which again leads to the fluctuations in power because of the intermittency of renewable energy sources, and also sees to that the voltage and current harmonics are within the limit. And they also perform time shifting operation. If suppose a microgrid is predominantly powered by a solar PV system, then you may not have power at the night. So in such a case, nocturnal demand is usually powered by or catered by the energy storage systems. So another operational issue or stability issue is the low inertia. As we all know, inertia of power system is very important to hold the stability, as we have seen in the frequency regulation in the previous, where the first, I'll slide through the slides, 1 minute. Okay, so inertia is the entity which holds the initial stability of a frequency event. So inertia determines what's the lowest frequency point of frequency nadir which is going to be, and it decides the stability of the system. If the system has low inertia, then no other go. It has to have energy storage systems or various other supporting mechanisms or spinning reserves to handle it. But still, the inertia of microgrids are very low because of the absence of rotating machines. As we have seen, it's predominantly powered by static sources like solar, PV, fuel cells, or any other energy storage systems except micro hydro, or variable speed wind turbines. One thing we have to notice, even though we have wind inertia and rotating components of the wind turbine, the inertia is hidden by the power converters. So we call it as hidden inertia. So what is the effect of these low inertia is the operation of rate of change of frequency relays even for small and balance, and these even results in operating of the frequency load shedding control when the frequency nadir goes below the stipulated limit or the relay setting. So the probable solution to low inertia problem is either virtual inertia emulation or hidden inertia emulation. Virtual inertia emulation, we have so many strategies where a power converter is used to mimic an operation of a synchronous machine. And hidden inertia emulation is to inject the inertial response with the stored energy in the rotor of wind turbines. So other economic issues include high capital investment. As we all know, to form a microgrid, we need investment in renewable energy sources and power converters, switch gears, everything. So it incurs a high capital investment, and grid parity is yet to be achieved. Grid parity is a one where the cost of energy from renewable energy is gauged with the cost of energy from the grid. If the cost of energy is less than the cost of energy from the grid, the grid parity is achieved. But most of the renewable energy sources are yet to achieve its grid parity due to various reasons like high 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 capital cost for the the sources itself. Then another important criteria is the long payback period. When any physical investment is like they consider payback period of a project. So usually the microgrid projects are distributed over 10 to 15 years, and the cost is determined by discounting the future cost to the present cost using a discount factor. So usually these systems have a payback period of longer than 10 years. So people don't invest much in renewable energy projects. However, you can see we have a strong economic justification here. The first thing is social cost of carbon emission, which is nothing but it is the marginal cost which we pay for the impacts caused by an emission of extra ton of CO2. It is actually the loss of revenue for any country, for that matter. And interestingly, India has the highest social cost of carbon, priced at $86 per ton of CO2, and with that, India faces a loss of about $210 billion per year. It's quite high for a developing country like us. And US is closely following with a cost of $50 per ton of CO2. So another thing is with microgrid, you can generate revenue by feeding power into the grid by considering the dynamic pricing signals, which is the point number 4, where we have energy arbitrage. That is the one I have mentioned before, where you consume the power from the grid when there is a low price period, and you inject power to the grid when there is a high price period. And probably the appropriate valuing of these revenue generation in a dynamic pricing environment, once the resources are available, will surely attract investments in microgrids. So we are coming to the end of this session. I'll just broadly discuss on the research avenues in microgrid. The first one is microgrid stability. Various algorithms have been developed, or various strategies have been devised to analyze the stability of a microgrid, starting from eigenvalue analysis to layup now stability criterion using transient energy functions. And the other important avenue is the energy storage systems, where people have started focusing on developing hybrid energy storage systems for various applications and devising control strategies for particular application, for that matter. And optimization techniques play a vast role in these research areas, where we can see heuristics and meta heuristics play a major role in energy management strategies, optimal sizing, and even for islanding detection techniques. Energy management strategies, as we have seen it, lies in the tertiary control level, and various algorithms incorporating meta heuristics, recent meta heuristics developments have been incorporated to optimize the performance of microgrid, so that the cost of energy is optimized in a microgrid. And optimal sizing is another factor which everyone should consider as a research area, because optimal sizing often results in a lowest cost of energy generation. And as we move further, we can see the microgrid is moving more towards an integrated energy system, from electricity to gas. It also incorporates combined heat and power plants, and also the use of gas for various purposes. So in future, we may become obsolete if we call ourselves as just an electrical engineer rather than calling us as power engineers. So protection of microgrids, again, a vast area which needs research attention. So finally, to conclude, let's see what's the relevance of microgrid in India. In October 2017, there were about 24.85 million houses yet to be electrified, and most of them were 70% of them were from Bihar, Odisha, Rajasthan, and Uttar Pradesh states of India. And now, as per Saubhagya dashboard, which is the movement which is driving the rural electrification. We have about 18,734 households to be electrified. Then comes the probable question: is Tamil Nadu fully electrified? And it's quite curious to know it's not, because still the hilly hamlets of Ariyar and Vetekar and Pudur in Coimbatore districts and various parts of Ooty or other hilly hamlets which are distributed throughout the state are yet to receive their lifeline power supply. And I have discussed with one of my friends from electricity board as well. He also said that it's yet to be electrified. So I don't know how far is 100% electrification to, as per our government reports. And as we see, the major barriers for 100% electrification is the geographical constraints. All these hilly hamlets are in the reserved forest area, where the forest department declined to give permission to erect high voltage transmission lines. And the second thing is affordability to grid supply. People can't afford to grid supply as they hardly have any earnings which for their survival, and high grid connection cost for electricity. And of course, after paying all this hefty amount, you need to have only an unreliable power supply in remote areas. So, being said, we have few successfully operating microgrids which are nothing but islands of excellence in the sea of mediocrity, where we have Darnai Solar in Bihar, which is of about 100 kilowatt capacity, where the cost of electricity is about 12 to 14 rupee per kilowatt hour, which is 3 to 4 times as that of grid electricity. But Sagar Island surprisingly has a lower cost, and microgrid installed by Amrita Educational Trust incorporates micro hydro turbine, and micro hydro turbine has a good potential for India where we have a good source in the northern regions of Indian states. So finally, I'll conclude with a short story of a village which is serving as an example worldwide and which is critically acclaimed globally for their business model to develop a self-sustained village or self-sufficient village. In 1996, they were a hunger and poverty-stricken village, and in due course, they have started investing in renewable energy systems. And firstly, they have incorporated with the 9 kilowatt biomass water treatment plant, which saved about 70% of cost of energy for them. And moving forward, a 2 kilowatt solar panel street lighting, where solar PV street lighting was installed to ensure safety of the village. And following which, in the next 10 years, they have even went to the level of buying a wind turbine from the nearby wind farm. As we all know, Coimbatore belt is going to have more wind farms, and they have purchased one of the wind turbine from those farms, is of 350 kilowatt capacity, and with that they were able to inject power to the grid after meeting their demands. So they were able to raise a profit of about 40 lakh rupee per year through this electricity trade. And in the due course, they have also formed 5 crore rupee corpus of 8,000 residents. And by 2020, they are self-sufficient now. This is the story for past 24 years, which they have gone through. So, to conclude, when the developing countries are fighting over reliable and resilient power supply, still the developing countries in India are fighting for lifeline power supply to cater for their basic needs and requirements. So thus, I hope microgrids are boon to developing nations like India and most of the countries in Africa for their remote communities and decarbonize the grid. I have attached the references which I've used to make the slides, and it gives a deep insights for you to understand all the concepts which I have discussed today. And it also includes few of my publications here. So thank you so much for patient listening for about past 1 hour. And I thank the Department of MEENAKSHI Sundarajan Engineering College for inviting me. It's always a pleasure to be back to the alma mater where I had my foundation of for what I am here now. Thank you. Thank you so much.
Thank you, Mr. Krishnakumar. The session was indeed very useful and informative. Hope everyone here agrees with it. I hope people would be exploring more and more in the years to come in this particular area. Now I request all the participants to post their queries in their chat box so that Mr. Bhaskar would read it up the questions to the presenter. Go ahead, sir.
Thank you, ma'am. We have a few questions posted in the chat. So I've collected a few questions. So the first question is from Pavan Pushya. So I'll read the question, Mr. Krishnakumar. The question is, why don't we encourage DC microgrid system and AC grid systems separately, at least at DG levels, so that performance can be improved and power electronics converters can be reduced? So this
Okay,
is
that's a good question actually. We can have separate microgrid switches of AC and DC in characteristics, but the main thing is most of our home appliances are of AC type, starting from our washing machines or induction fans or ACs which operate in AC. We don't have much DC loads except our appliances or electronic components which requires DC. So that's one point. And another point for DC microgrid is the protection. We need to change the protection system of the distribution system in order to have incorporated DC microgrid into a picture. Because today's protection systems are based on our AC voltage or current or AC power for that matter. So DC needs to be, has a good potential, but in that case, hybrid microgrid makes more sense, where you can have both AC and DC loads connected together through an interlinking converter. You won't have a problem of reconfiguring your own, distribution system to incorporate the DC sources for as directly. I hope it's clear now.
Yeah, I hope it would have been clear. So I'll go with the next question. The next question is from Satyanarayanan. The question is, how does inertial response and primary control differ for a VSC based DG source?
Okay. A conventional voltage source converter, we don't have inertial response. Okay. So primary control comes into picture only when system arrests the frequency. To arrest the frequency variation, we need inertial response. This inertial response is usually provided by these rotating machines. And in today's scenario, most of the voltage source converters operate as current control devices, or which operates in PQ control mode. They offer zero inertial response. They even hide the inertial response of rotating components like variable speed wind turbines. So they won't have much effect on the inertial response, but have a good primary response. They can regulate the frequency. In order to have a good inertial response, people have went into research on virtual inertia emulation, which is a hot topic of research now, where we have various configurations like synchronverter, virtual synchronous generators, or even virtual synchronous machines for that reason, where they try to emulate the behavior of a synchronous machine so that they have they can operate the voltage source converters as a synchronous machine itself without modifying the control strategies of a centralized grid. So the final answer is voltage source converters, which are predominantly current control, doesn't exert any inertial response. Rather, it hides the inertial response of even the wind turbine. Hope it answers your question.
Okay, Krishnakumar. I'll move on to the next question. The next question is from Darini. The question is, what does the utilities take in microgrid adoption?
Okay. Actually, when you look at the utility, level, here in India, everything is monopolized, where the state transmission and distribution company owns the right. We don't have any rather they don't have any role to play in this, because the government has to make some schemes so that people adopt microgrids or adopt distributed generation. Only then utility will respond to these changes and make necessary changes to it. And even today we have in Tamil Nadu, we have renewable energy department separately in the electricity board itself, where they try to develop more schemes, disperse the subsidies so that people adopt rooftop or distributed generation, so that they can go for localized generation. So as a company, they always try to maximize their profit. So they don't focus much on the subsidies, because the major thing for people to adopt microgrids or to have a microgrid. So subsidies can come into picture only with the government's intervention. So I hope government should intervene in such a case.
And we have a lot of questions coming here. We'll have a couple of questions here, and we can proceed with this question and answer session in the Telegram group. So we'll be posting you the link to the Telegram group. So let us continue the discussion even after the session ends here. So we'll go with a couple of questions more. This question is from Thiruvenkata Swami. The question is, why we are not able to manage wind power and grids due to overproduction? Maximum of the time we are stopping the wind farms. Is there any new storage system to manage this?
Okay, that's actually a good question. At grid level, India doesn't have any grid level storage systems so far. Our grid level storage systems are only pump hydro storage systems, which are tried and tested for over a century. So I think it's because of the lack of energy storage systems. And people are talking about lithium ion is the future of energy storage, but I don't go with that point, because Earth's crust doesn't have an enormous amount of lithium ion to support its application in both electric vehicles perspective and grid perspective. So we need to invest more in building pumped hydro storage, thermal energy storage, and why not compressed air energy storage, which are of high energy capacity, so that the curtailment of renewable energy sources are limited, and we can maximize the profit by storing the energy during surplus generation. So for that, we need more investment in hydro. And again, when large-scale hydro comes into picture, there's so many social issues will come into picture, starting from rehabilitation of the local community and the environmental or ecological effect. So these pertain with large-scale energy storage systems. If you go for large-scale battery storage systems, again, batteries have low life cycle. It can last for a few years, but as opposed to mechanical energy storage systems like pumped hydro, compressed air, or even thermal energy storage, they have high life cycles, and lifetime is very high. And also their life cycle cost, which is the operation and maintenance cost throughout its operation, is quite low. So I think mechanical energy storage systems has quite a good potential to limit the wind energy curtailment.
Okay, so the next question is from Ashish Shukla.
1 minute, sir. 1 minute. Actually, if you look into the slides back, I have discussed most of the high energy storage systems, where you can go to the reference, ponder upon, and grab the crux of each energy storage, so that you can get a deep insight of each energy storage and its application on a whole. Yes, sir, please.
So next question is from Ashish Shukla. The question is, as per the slide in the beginning, losses in the Indian power system are high. What is the reason for such low efficiency? Also, what are the cost effect of these energy storage devices on our power system?
Okay, I have mentioned in the slide, but I forgot to discuss here. It is not only transmission losses, it is called as all technical and commercial losses, by which it means it doesn't account only for the losses at the transmission level. It also accounts for power theft or any other unaccounted power withdrawn from the grid. And you know how Indian political system or any public meeting in India operates. So they just stop in the power from the line without any metering, and all these accounts for losses in the system, and the company or the distribution company usually accounts it as losses. So that's the reason for the high losses. It's not alone the technical losses, it's also because of the commercial losses of power. And the later part of the question, so can you please repeat the later part of the question?
So the question is, I'll repeat the question. As per the slide in the beginning, losses in the Indian power system are high. What is the reason for such low efficiency? Also, what
Yes,
are the
okay.
cost effects of these energy storage devices in our power system?
Okay. The cost estimation for each energy storage system differs vastly, and each requires different cost estimation, where our pump hydro storage has lowest cost for storage, followed by battery energy, not battery, I think it's compressed air energy storage and thermal energy storage, and comes the battery. It incorporates both the capital investment and also the life cycle cost of each energy storage. So when you consider only the capital investment, you can see hydro storage is hydro storage has a very huge investment. But when you look into the lifetime of its operation and its life cycle cost, the cost of pump hydro storage is very low. And I think one of my references deals with uh, comparison of pump hydro storage and battery. For that reason, you can go into that reference and ponder upon where pump hydro storage has a lower level of cost of energy storage. Yes. Yes, the next question, please.
We'll go with the one final question, small question. So,
Yeah.
what could be the maximum capacity of a microgrid? So, this question is from Viswajit.
Oh, okay. So far, people haven't come with a standard value of microgrid efficiency, but with its technical details into place, you can achieve as high as 60 to 70% efficiency with localized generation, as opposed to 30 to 40% with centralized grid networks. Because the centralized thermal power plant's efficiency is just 20 to 30% when it covers all the losses incurred in the thermal system, in their steam generation system, and in the uh, turbine system, and also in the cooling system, because all these incorporate various machines to operate the power plants, where they have various pumps to pump the feed water pumps. So the efficiency of thermal power plants is very low compared to our renewable energy based microgrids, and it can still cater for 60 to 70% of the efficiency.
Okay, thank you, Krishnakumar. Hope the participants would have got clarified with their doubts. So we can keep this discussion continued in our Telegram group, and also do mail us so that we'll ask our speaker to answer your questions. Now I call upon Gayatri ma'am to take over the session further.
Thank you. Thank you, Mr. Bhaskar sir. I would now like to express our heartfelt thanks to our speaker, Mr. Krishnakumar, for his valuable session. And I hope after this session, everyone would look forward to putting some of the techniques into practice in this particular area. Thank you once again, sir. Now, a small announcement to the participants. The quiz cum feedback link would be provided in the chat box. I request everyone to take the quiz, which is considered as attendance for today's program, and kindly give your feedback too. Now, I repeat it again. I request everyone to take the quiz, which is considered as attendance for today's program. Tomorrow's event link would be sent to you all by mail and also via Telegram app. I thank all the participants for your cooperation throughout. Thank you all once again. Looking forward to meet you all tomorrow for the second webinar session. The feedback link and the quiz link is posted now. Please have a look at it, all of you. Just take time to fill the feedback link properly. The quiz and feedback link would be posted in your checkbox. I request all the participants to take the quiz, which is considered as attendance for today's program. The quiz and feedback link would be provided in the chat box. Please join Telegram app for more updates. The quiz link is posted in the checkbox, the chat box. Please have a look at it. I request all the participants to give in their feedback of the today's session.
The feedback and quiz link has been posted in the chat box. Please refresh your browser and just look at the chat. There are multiple links being posted in the chat box. And also, we would like to inform you that the feedback links will be sent to you through mail, and also it will be shared in the Telegram group.
Any queries regarding problems in registration? You can just mail us at triplefew2020@gmail.com.
Thank you, participants. We'll wind up this today's sessions. We'll keep you posted in our Telegram group, and we'll be connected with you through the mails. So we'll send you the updated mail for tomorrow's event. So please be updated in the Telegram group, and also please be checking your mail. Thank you.
Bhaskar, shall I close the session?
Yes, ma'am.